Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fourth video of Chapter 8 Newton's Laws. At the end of this video, you're going to be able to derive the equations of motion of a free falling object, mainly on the vertical launching. In the last videos, we have mentioned the definition of inertia, mass, Newton's first law, Newton's third law, Newton's second law, and finally the tension force on a massless rope. Before we start, it's important to give you some information about antiderivatives. Antiderivative is the inverse derivative of a function and is also called primitive. It reverses what the derivative does. It has a mathematical symbol and it's read as capital F of t is the integral of a function, small f of t dt. One function has many antiderivatives, but they all take the form of a function plus an arbitrary constant. We are going to consider the antiderivative of the functions that we will need in this lesson. If we have a function f of t equals to a t exponent n, the rule says that its antiderivative is capital F of t equals to the constant a multiplied by t exponent n plus 1 divided by the new exponent n plus 1 plus this arbitrary constant c. Let's verify it and make its derivative. We multiply the exponent n plus 1 with a function a over n plus 1 t exponent n plus 1 and subtract 1 from the exponent. By reducing n plus 1 with n plus 1, we can find the answer as a t exponent n, the same as the one we started with, but where is c? The derivative of c is 0. Let's think together with some examples that we may work on through this lesson. If a is 0, what function has a derivative equals to 0? It is the derivative of a constant. Thus, the antiderivative of this 0 is just a constant. This is easy to verify. Now, what if the function is vx equals to 4, which is constant? If we want to follow the general antiderivative rule, this function means that it is 4 times t exponent 0. Placing n by 0 in the first antiderivative rule, we can get the antiderivative as x of t equals to 4 into t exponent 0 plus 1 over 0 plus 1 plus c2. Now verify it. The derivative of 4t plus c2 is just 4. In another way, you can ask yourself, what is the function whose derivative is just 4 or constant? It is 4t plus constant. Finally, the antiderivative of 10t, and we know that t here is exponent 1. Then, following the general rule mentioned above, we can say that it is 10 t squared over 2 plus c, which is 5 t squared plus c3. And to verify it, make derivative for this function, then we can say it is just 10t because the derivative of c is 0. Note that the constants c, c1, c2, and c3 are determined using the initial conditions. For example, c2 is x at t equals to 0, which is x0, and c3 equals to y at t equals to 0, y0. In the next example, it will be more clear to understand it. Sample example. Determine the time equations x of t and y of t, knowing that the acceleration vector, the initial position, and velocity vectors are respectively a vector equals to minus 10j r0 vector equals 2i vector plus the 3j vector, and v0 vector equals to 8i vector plus 7j vector. In order to solve this question, we're going to use this table that we're going to call it antiderivative table. First, let's fill in the components of the acceleration vector along x and along y. After that, we're going to use the antiderivative to find v vector and r vector. Now, ax is 0 since they mentioned that it is just minus 10j vector. So ay is minus 10. Now to find vx, it is constant. Why? Because the antiderivative of 0 is constant. Now what is this constant? To find this constant and others, we should write the initial conditions on the copybook and try to find their components, starting with r0 vector equals 2i vector plus 3j vector. This means x0 is 2 and y0 is 3, while v0 vector equals to 8i vector plus 7j vector. Thus, v0x is 8 and v0y is 7 in meters per second. Now let's go back to the table. What is vx then? Since it's constant, then it is equal to the v0 at x, and it is 8. To find vy, then we go back to the rule, and it will be vy equals to minus 10 times t exponent 1 plus c1. So now what is c1? We should go back to the initial conditions, and it is 7. So it is written as minus 10t plus 7. Now what about r vector? The x component is the antiderivative of vx. Thus, the antiderivative of a constant is 8t plus x0, which is 2. What about y? Y also is the antiderivative of minus 10t plus 7, which is vy. The answer is minus 5t squared plus 7t plus 3. From now on, the constants can be written as x0, y0, v0x, and v0y in the time equations. Now we're going to start with the free-falling body. To understand the concept of a free fall, we are going to observe two different experiments and make some comparisons, starting with experiment 1. A bowling ball and a feather are set to fall together from the same height at the same time. Which one do you expect will reach the ground first? Let's watch this video, which is extracted from the experiment performed by Brian Cox in the world's biggest vacuum chamber. This chamber is used to test spacecraft in the conditions of outer space. He took a heavy object as a bowling ball and a light one, which is the feather. He dropped them at the same time to see which one is faster. What do you think? Now in this case, the feather fell to the ground at a slower rate. The bowling ball then reaches first. What are the forces acting on each of them? Each is subjected to its weight and to a resistance. In the second experiment, the chamber is evacuated from air. Which object will reach the ground first? Do you think it's the bowling ball so? Let's watch the following video with Brian Cox again. The same experiment is repeated after evacuating the chamber from air. From the same position, the feather and the bowling ball are released. You can see their motions while it is shown in slow motion. Wow! Did you expect this result? What are the forces acting on each then? What can we say about the position and the velocity of these two objects at an instant t? There is no air resistance, and each body is subjected to its weight only. Despite their different masses and shapes, they have same position and equal velocity. To make conclusion, let's sum up the results. For each experiment, let's write the forces acting on the bowling ball first, then on the feather. Which one reached first? The ground. In the first experiment, the bowling ball. In the second one, both arrived at the same time. What about the velocity? In the first experiment, the bowling ball was faster. In the second one, they had the same velocity. Now, which one deserves to be called free-falling body? Perfect. It's not that one in the first experiment. It is in the second one. The free-falling object, then, is any object moving under the action of its weight only. Actually, from the last two experiments, we get that the bowling ball and the feather have the same motion when they fell freely, independent to their mass or their shape. Can this result be found analytically as the experimental result? Now let's start. We know that the only force acting is weight. Then, applying Newton's second law, we have W vector equals to ma, mg vector equals to ma vector, thus a vector equals to g vector. This expression shows that the acceleration and so the motion is independent of the mass and of any physical quantity related to the volume or the shape. So, shape doesn't affect the motion and the mass doesn't affect the motion, in agreement with experiment 2. From this equality, we can recognize that G can have a unit, meter per second squared, while we used to write it as Newton per kilogram. For that, G is called gravitational acceleration. Some examples on the free-falling objects are the oblique launching of a particle, the horizontal launching, the upward vertical motion, and the downward vertical motion, besides the motion of the satellites. Neglecting air resistance and the forces exerted by Sun and other planets, the balls and the satellite are freely falling objects since each is subjected only to its weight. This lesson, we are going to talk about all these cases except the motion of the satellite. To sum up, in this video, we have mentioned that a free-falling object is any object moving under the action of its weight only, and a free fall motion doesn't depend on the mass and the shape of the object. This is the end of the fourth part of this chapter. Thank you for watching.